In the name of the Almighty, the Compassionate, the Merciful. Again, we are going to pursue our study of the application of the derivative. In fact, there are so many applications, like we said in our last lecture. Among them, actually, comes one of the methods which are very efficient and capable for calculating limits. This is called a L'Hopital rule. So, in fact, in this lecture, we're going to display this L'Hopital rule as well as other applications of the derivative. First of all, we're going to speak about the indeterminate quantities, and then the Cauchy mean value theorem, furnished the basis of which one can deduce L'Hopital theorem, and then L'Hopital rule, and finally the convexity and concavity of functions. First of all, students know well that there exists 7 indeterminate quantities. We mean by indeterminate quantity a quantity which can be equal to any other one. For example, when you have, when you write 5 times 0 is equal to 0 times 7, and is equal to 0 times square root of 2, etc., and is equal to 0 times 0. So in fact, the algebra tells you that 0 over 0 can be very well 5 over 7 or 7 over 5, etc. So in fact, it's indeterminate. It does not. It may not be assigned a certain quantity, and there are 7 of them. The most important, the one which we encounter most, are either 0 or 0 or infinity over infinity. But the others as well are, you can encounter, for example, 1 over to the power infinity is like when you try to take the limit of the sequence which represents the Euler number E, etc. And in fact, this 0 over 0, you encounter it very well when you try to obtain the derivative of a function. The derivative of a function, you try to take the limit of this quotient of this ratio here, and if you take the limit of the numerator, you find it 0 from the basis of continuity, because a function cannot be differentiable unless it's continuous. So actually the numerator tends to 0 from continuity, and the denominator, when x tends to a, equally tends to 0, so you find a quantity which is 0 over 0. And this, the one in the bottom here, it's when you take the limit when n tends to infinity, you get 1 to the power infinity, which is should be in fact E, etc. So actually these indeterminate quantities, you encounter them when you seek to determine a limit and first sight you get a 0 over 0, so that this is not correct, and you wish to pursue with other ways for obtaining specifically this particular limit or the exact value of this limit. And in fact, in order to obtain limits of function of this sort, you rely upon a theorem called L'Hopital. But this, in fact, theorem, which is L'Hopital, and in fact it's not his, because it was discovered by Bernoulli, his tutor, but because L'Hopital was the first one to write a book on calculus, so because he incorporated the theorem in his book, so it was attributed to them, but in fact it's not his, but this is immaterial in any way. But previous to him, or actually it's after him, because Cauchy came later, but the proof of L'Hopital relies upon a simple theorem called Cauchy theorem. This is in fact a theorem like very similar to the Cauchy, to the mean value theorem which we saw before. It tells you the following: if f and g are both continuous on the closed interval AB and differentiable on the open interval AB, then and g dash prime of x is not equal to 0 for all values of x in the open interval AB, then there must exist a number zeta in AB such that the following is true: that f of b minus f of a divided by g of a minus g of a is equal to f of theta divided by g dash, f dash divided by g dash at the point zeta. In fact, here we have to notice something. First of all, this looks very much like the mean value theorem. Why? Because if you substitute f of b minus f of a by b minus a f dash of eta, and then you cancel out b minus a from both numerator and denominator, you end up with this form. But the difference is that this may not be equal, zeta 1 and zeta 2. This is one thing. The other thing is that g of b and minus g of a is not equal to 0, because if they're equal to 0, according to Rolle theorem, the function g is differentiable and continuous on AB, and therefore if it equals if it is equal at two different values of a and b, like gb is equal to g of a, so therefore there must exist a point at which g dash vanishes. But since here g dash of x is never equal to 0, then there is no worry that g of a and g of b are equal. And this actually theorem, this result, you can write it in a better way, this way. You can say that here f of x minus f of a divided by g of x minus g of a is equal to f dash at point theta divided by g dash at point zeta. And this theta here is between a and x. This is in fact the same result we have it on the slide, except that you say that both f and g are continuous on the closed interval ax and differentiable on the open interval ax. Now, from this theorem, in fact, you can obtain a L'Hopital rule directly. How? Is that you construct another function f of x equal to f of x minus f of a, and at the same thing you construct another one, you pose another function g of x equal to g of x here minus g of a. And since you know very well that f and g are differentiable and continuous respectively on open interval x and closed interval x, therefore capital F and capital G are the same, have the same property. But you note something here, that limit of f of x when x tends to a is 0. Why? Because the limit of f of x is equal to f of a, because f is continuous. And therefore, when you take the limit when x tends to a, this vanishes, and therefore limit of f of x, capital F of x is 0. And same thing applies to capital G of x. So in fact, these expression here that one sees here, you can write it in a different way. You can substitute the numerator by capital F of x. So in fact, we have this formula. Capital F of x divided by capital G of x is equal to f prime, which is the same as f dash prime of eta divided by g dash prime of eta. And here, capital F of x and capital G of x are both continuous on ax and differentiable on ax. And if you wish to apply the limit then of this quotient, capital F of x over capital G of x, when x tends to a from the right, you end up with what? With f dash of eta over g dash of eta. And here again, you take the limit when eta tends to when eta tends to a as well from the right hand side is like from like x tends to a. So instead of writing eta and eta, is like in books they prefer to write, for example, x, and you take the limit when x tends to a from the right hand side. So it tells you here that if you have two functions, the quotient of two functions f and j, that they are continuous on the closed interval ax and differentiable on the open interval ax, the limit when x tends to a, if you find that the limit of the numerator is 0, as well as the limit of denominator, as we have seen before in the previous paper, because both small f and small g are continuous at a. So if this tends to 0 and this tends to 0 simultaneously, then you may substitute this limit by the derivative of the first one divided by the derivative of the denominator to obtain a formula of this sort. This is in fact L'Hopital rule. L'Hopital rule tells you that the limit of f over j is equal to the limit of f prime over g prime. The only difference, in fact, from L'Hopital rule, this is in fact can be obtained from Cauchy formula. The only difference is that L'Hopital tells you that capital F and capital J, or small f in the slide, same thing. If we replace capital F by small f, I mean, it's only a matter of symbols. The only difference between this and L'Hopital is that capital F and capital G are differentiable except at point A, which is correct, but they may not be continuous at A. Here they are continuous at A. So all you have to do if you wish to make them comply with Cauchy is that you can write it this way. You can give it a value here 0. So in fact, this is the second rule of you define another function capital F, so that capital F becomes here now continuous at the point x equal to A, and the limit and it gives the value 0. So the limit of f of x, because it is 0, we know this before, so the limit is equal to the value of the function. Therefore f tilde is continuous on the open, now it's continuous on the closed interval AX. And therefore, the same applies. L'Hopital rule now, we can come to L'Hopital rule and say that this is L'Hopital. Either you use this as L'Hopital rule or the other one. The only thing that they both comply to each other, and you can, one is the replica of the other, and we come up here now with L'Hopital rule. So L'Hopital rule, in fact, is another way of writing Cauchy formula. It says, it tells you this: if f and j are two functions differentiable on AB, except perhaps at point C, of course C could be an interior point to AB, or an end point could be A, same thing. And if the limits of f of x and g of x simultaneously tend to 0 or tend to infinity. In other words, and this is one thing which is important, L'Hopital only works for those indeterminate forms, the two indeterminate forms, 0 over 0 or infinity over infinity only. And any other indeterminate form, you can transform it into these two forms and then apply L'Hopital rule. And so if these limit of g of x and f of x tends to 0 simultaneously or to infinity simultaneously, then you might substitute the limit of f of x over g of x by the limit of the f dash over g dash. So to apply now L'Hopital rule, all you have to do, you have to make sure that there are two conditions which are verified. The first one, that they, both the numerator and denominator, are differentiable in the neighborhood of the point A simultaneously, and that both f and j are differentiable in a deleted neighborhood of the function. They're differentiable in a deleted neighborhood of A, the point at which you seek to determine the limit, and both tends to 0 simultaneously. And these are the only two conditions which you wish to verify, and therefore you can proceed with L'Hopital directly. But there is one thing you have to make sure of, is that, as we said, since they are both, they first have to both tend simultaneous to 0. For example, suppose, for example, this is an example which shows to the student that you have to verify both conditions. Suppose f of x is x plus 18 and g of x 3 minus 2. So, and you wish to take the limit when x tends to 0. All you have to do, you replace x by 0 and you get x equal, you get the limit is equal to 9. Here the limit is equal to 9 is the right limit. But if you take the derivative of the numerator of the denominator, you get third. This is wrong. Why this is wrong? Because before applying L'Hopital rule, which is the derivative over the derivative, you have to make sure first that the limit, that both limit tend simultaneously to 0. But in fact, both limit, they do not tend to 0. And therefore, you can here L'Hopital rule doesn't function. So L'Hopital rule, in order to function, you have first of all, for example, in this example, you have to when x tends to 1, here this one, the numerator tends to 0 as well as the denominator, and because the denominator and numerator, they are both differentiable in a deleted neighborhood of 1, so you can apply L'Hopital rule. Now you can say the quotient is the indeterminate form, 0 tends to the indeterminate form 0 over 0, and therefore you can very well differentiate the numerator and denominator simultaneously. The derivative of this is 3x squared minus 2, and the derivative as well of x minus 1 is 1. So the limit, this limit is equal exact to this limit. When you apply x equal here to tends to 1, you get 1. So actually this now works perfectly, and you can apply L'Hopital rule so long as the two conditions are verified. Same thing here. Calculate the limit here. Limit when x tends to 0. You directly see that the numerator, this tends to 1, plus 1 minus 2 is 0. And the same thing here, 1, so 1 minus 1 is 0. And therefore, and 1 minus cosine, as well as numerator, are differentiable in a deleted neighborhood of 0. And therefore, you can apply, and they tend both simultaneous to 0 over 0, so you apply the theorem. And the theorem tells you that the limit, this is the derivative of the numerator alone. You don't differentiate the whole quotient. And this is one common mistake. No, you differentiate the numerator alone and the denominator alone. So the derivative of the numerator is this, and the denominator is this. When you take the limit when x tends to 0, but here again you get 0 over 0. Doesn't matter. So long as the theorem is verified, here again, the conditions of the theorem are verified, you go and differentiate again. When you differentiate again, this time it stops, because this tends to 1 and this tends to 4 plus 4, 8. So this is the limit. And these things how they go. Calculate the limit of x ln x when x tends to 0 from the right-hand side. Here there is a problem. Here the limit tends to what? 0 times infinity. So you cannot apply L'Hopital. L'Hopital only applies to 0 over 0 or infinity over infinity. So what you do here is what? You put it in the form which is amenable to L'Hopital rule. You put it in this form, ln x over 1 over x. Now when x tends to 0, this one goes to infinity, and this one as well. So you have infinity over infinity, and then you can apply L'Hopital rule. So all you have to do is you differentiate, since it's ln x over 1 over x, you differentiate ln x 1 over x, you differentiate 1 over x minus 1 over x squared, and then you apply the limit. The limit here is what? The limit here is simple, because this limit you can invert 1 over x squared to finally obtain the limit of minus x. You find here it's simple. This is the limit of minus x, and when x tends to 0, it gives you 0. Again, evaluate sine x to the x when x tends to 0 plus. This is a transcendental function, and when x tends to 0 plus, you get 0 to the power 0. Again, you cannot apply L'Hopital. You have to put it in a form amenable to the application of L'Hopital. So what you do is that, yes, this is the indeterminate form 0 to the power 0. This is one of the 7 indeterminate forms. In fact, we said there are 7 of them. Only 2 of them are one can use L'Hopital to evaluate the limit, only in 2 of these 7 forms, and the others are you can transform them into these 2 forms. For example, here, if you substitute y is equal to sine x to the power x, in other words, you suppose that sine x to the power x is equal to y, and then you start by applying the logarithm. Then the logarithm of y is equal to what? Is equal to the logarithm of sine x to the power x. But the logarithm of sine x to the power x is equal to what? Is equal to x ln sine x. So in fact, ln y from this expression is equal to x ln sine x. Now you start by applying the limits. But the limit here, you cannot still apply L'Hopital rule to the right-hand side here, because you get here what? You get, when the x tends to 0, you get 0 times infinity. So you have to put it in a form which is amenable to L'Hopital. This form here, you can put in this form, ln sine x over 1 over x. Now when x tends to 0, you get what? You get infinity over infinity. So now you can apply L'Hopital rule, and since you can apply L'Hopital rule, you differentiate both the numerator and the denominator separately, and then you check for the limit when x tends to 0. When x tends to 0, here you get what? You get again what? This is infinity over infinity, or what? No, you can, in fact, you can put it in a form which is suitable for the limit instead of applying L'Hopital another time. You can, in fact, put it in this form. Yeah, and this form, actually, when x tends to 0, you get what? You get 0 here. Because this is 1, this is 0. But we know that the limit of sine x over x, instead of doing L'Hopital rule, of course, you still can do L'Hopital rule here. You can apply L'Hopital rule. But again, since this tends to 1, you get 0 over 1, you get 0. This 0 is what? Is the limit of ln x, limit of x ln sine x. Which is the limit of ln y, but you don't want the limit of ln y. You need the limit of y, which is sine x to the power x. So what you do, you know that the logarithmic function, and this we have established before, is continuous, and therefore this is one of the function of the limits and behavior or properties of the limits, that when you see an outer function which is continuous, like the ln, you can say that the limit of ln something is equal to the ln of limit something. So in fact, now we have established that the limit ln y is 0, and since we can take ln out of the limit of the bracket here of y, it becomes equal to ln limit y. So in fact, we end up with what? The ln, the logarithm of the limit is equal to 0. So what's the value of the limit? The logarithm of something is 0. This something must be equal to 1, because this is the value at which logarithm is equal to 0. So in fact, it means simply that the limit of y must be equal to 1. And that's it. And this is what we seek actually to calculate. Your limit is equal to 1. Again, if you have, for example, a limit of this sort, when x tends to 0, you get what? Infinity minus infinity. You cannot apply L'Hopital again. So it doesn't matter. it's infinity or minus infinity is one of the indeterminate forms, but all you have to do is that you put it in a form which is which tends to 0 over 0. This form here, since it is the L'Hopital conditions are verified because they tend to 0 over 0, and they are both differentiable in the deleted neighborhood of 0. So you can actually apply L'Hopital and you differentiate both numerator and the denominator, but separately to obtain here cosine x minus 1 divided by the derivative of x sine x, and then you apply the limit when x tends to 0. But again, there is a problem. When x tends to 0, you get 0 over 0. It doesn't matter. You differentiate it twice to obtain to obtain the limit as equal to 0. And actually, this is the way how things go. In order to apply L'Hopital, it's easy. L'Hopital tells you that if you, by any chance you have the limit of the numerator and the denominator both tend simultaneously to 0, and both of these two functions verify the other conditions which invokes that both are differentiable in the deleted neighborhood of the point at which you seek to calculate the limit, then all you have to do is that you substitute for the limit as the limit of the quotient of the derivatives. So all you have to do, which is actually the simplest way of calculating limits. It's actually, in fact, superior than the ways, the methods that we have already discussed before. This one here, all you have to do, because derivative is easy for the student to do it, you differentiate the numerator as well as the denominator, and you end up with the limit to calculate the limit which you seek to obtain. The only thing which you have to make sure are two things to apply L'Hopital. First, that both numerator and denominator, they have to both simultaneously tends to 0, or 0 over 0, or infinity over infinity, because we said before that you have 7 indeterminate forms. So L'Hopital works only for the first two, 0 over 0 or infinity over infinity. But what about the others? It's simple. All you have to do is to find some way or the other by which you can transform it into a way amenable to the application of L'Hopital rule. Like, for example, in this example here it was infinity minus infinity. So all you have to do, you put it in a form in which you find out that they tend both the numerator and the denominator to 0 over 0, and therefore you can apply from then on you can apply directly L'Hopital rule. Now we move to another application also of the derivative, the problem of convexity, concavity, and extrema, etc. Extrema probably we may be able to give it a separate lesson because it's important. But anyway, the first one, which is convexity and concavity. First of all, we have, when we spoke about in our fourth lessons about the classification of functions, we realized that functions they are behaving in a certain manner. Like, for example, we said that they might be even, odd, monotonic, increasing, decreasing, periodic, etc. So actually, the way of studying instead of saying that the function is monotonic, increasing, and f(x2), like, for example, here is greater than f of x1, like it shows on the graph here, you better discuss, you better investigate the derivative. And if the derivative is positive, it means that your function is increasing. If the derivative is negative, it means it declines. This is the way of it goes. In order to investigate whether your function is increasing all the time, it means that the derivative is positive, because the slope is positive, and then you climb your graph. So if it is increasing function, f dash must be greater than 0. Of course, if it is equal to 0, then there is a point of a stationary point. If f of x2 for any value of x2 greater than x1 it's constant, in other words, this function is constant, then it means that your f dash is 0. Why? Because how would you calculate f prime of x? It's the limit of f of x2 minus f of x1 divided by x2 minus x1, and you take the limit when x2 tends to x1. So since f of x2 is equal to f of x1, it means that the derivative is 0. So when you want to express yourself as saying this function is constant, you say that derivative is 0. Or if the derivative vice versa, the derivative is 0, it just means that your function is constant. Again, if f of x2 is less than f of x1, If f of x2 is less than x1, it means that there is a kind of decline here, that you are going down the hill, and f dash is negative because f of x2 is less than f of x1, and x2 is greater than x1. So the quotient of f of x2 minus f of x1 divided by x2 minus x1 is negative in this case. And since this is negative, and there is a theorem saying if the function is negative, the limit is also negative, so actually f prime is also negative. And since f prime is negative, it just means that this function is a decreasing function. Now, this is a remark that we should state. This remark, sometimes the function is increasing. For example, when, as it shows here on the screen, both functions are increasing, this one and this one. But there is a difference between the two. The difference here is that the slope of the tangent at the beginning is slow, and then it accelerates. As if, for example, you have an acceleration. Your function, for example, you take your car and you drive, and then you begin by accelerating. You start from rest. You begin from rest, and then you speed up. So when you speed up, you're accelerating. So the velocity increases. Of course, you are gaining distance. You are gaining ground. Because your distance, you travel. Yes, you don't go back, but your speed increases. So here, actually, this function here, the f of x is monotonically increasing. But there is one other thing you notice, that f prime of x increases as well. F prime is increasing. You start with a small velocity, and then you accelerate. So your velocity is increasing. And since your velocity increasing, then your f double prime must be positive, because your acceleration is positive. If you are decelerating, then your acceleration is negative. Since your acceleration is negative, meaning that your velocity is, you are slowing down. You are slowing down your speed. So these two functions, in fact, both of them are increasing functions, this one and this one. But what is difference? The difference between the two is that in the first one, f prime is increasing, where in the second one, f prime is decreasing. Here you start with a higher velocity. Your slope is great, and then your slope you decline. Your slope declines a little bit. It lowers down. Your slope becomes smaller. Like we said before, you have you decelerating. Since you are decelerating, then you are slowing down. Since you are slowing down, then the derivative is smaller here than here. So in fact, these we call these functions in the literature, in European books, I suppose. This is called convex, and this is called concave. In some in the Western bloc, in the Eastern bloc, I'm sorry, they call this convex upwards and this convex downwards. Whereas in the American books, I suppose this is called concave below, and this is called concave upwards, and this is called concave downwards. But I think the best terminology is to say that this is convex and this is concave. So convex curves are those which the function is increasing, but in fact it may be decreasing as well. But if it is increasing, f prime is decreasing, whereas here, if it is increasing, f prime is also increasing. So in order to differentiate between concave and convex, they tell you how can you know that this curve is concave or convex? Because actually concavity and convexity applies to the curve, the graph, not to the function. But the function, it's the derivative, which I suppose, which tells you how the behavior of such function. So here, for example, for a curve to be concave, whether it's increasing or decreasing, here the tangent to the graph is below the graph. Here the tangents at the beginning and end is below the graph. Same thing here. The tangents are below the graph in order for the curve to be concave. Whereas for a curve, if the curve is convex, then you find that the tangents lies above the graph. Here also, whatever, irrespective of whether the function here is increasing or decreasing. Both of these curves, in fact, the function is increasing. The function is increasing, and here it is decreasing. but in both, the curve is convex. Why? Because the slope lies above the curve, the graph. In fact, both have the same behavior, have the same quality. How? If you calculate the first derivative here, the first derivative is high, then it becomes low. Here it is high and becomes low also because it's negative and negative. But the negative here, then for example, it goes from -3 to -7. So actually it lessens in value. So in fact, f double prime here is negative, and here also it is negative. Whereas here f double prime are in both positive. But you remark it by the tangent if you wish, as we said just now. Also, you may want to know what the meaning of inflection points. Inflection points are those points at which the function changes from behavior, from the concavity property into convexity. If f is continuous, and it changes, the double derivative changes sign from here, for example, from negative to positive, then we say that there is a point of inflection point. So inflection points occur between two regions of convexity, then concavity, or the converse, and usually we notice this point of inflection by is that it has the property that the double derivative is zero or does not exist. So a point of inflection is the point at which it's an interior point to the graph, at which f double prime is zero or does not exist, and then it separates two regions, one in which the graph is convex, and then it becomes concave, or the converse. Like for example, here it was convex then concave, but here it is concave then convex, and this again is an inflection point. This is the meaning of inflection point. For example, if you wish to study this curve, this is a sine curve. This is a periodic curve, and a periodic curve of this sort, it must have a region in which it increases and in which it decreases. Again, does it have an inflection point? Is it convex? Is it concave? All this kind of relation, we wish to investigate it in the region from 0 to 2 pi. Of course, if you take other regions, you might as well do the same thing. But this is a replica. It will be a replica of this region. This is the period of sine x, and we wish to investigate such curve. So this is how it goes. First of all, we draw the graph of f. The graph of f, this is the blue one. This is the graph of f. And f prime, which is the derivative, which is what? The derivative of sine is cosine. In fact, this is the cosine, which is the brown one. The brown one here stands for the graph of the derivative of sine x, which is cosine x. Of course, at the points which is 0, sine is maximum, and vice versa, because there is a time lag. There is a lag of x by pi by 2. And then the green one is the double derivative of sine x. The first derivative is cosine. Again, it's minus sine. So the double derivative is minus sine. So actually, you get a 180 out of phase. The green and the blue. The blue is the function sine x, and this is minus sine x, which is the double derivative of the sine. Now, if we wish to know where are the intervals of increase, the function increases till pi by 2. So the derivative is positive, and this is why the derivative here is positive. And then the derivative is negative in between pi by 2 and 3 pi by 2. So it tells you that the function lessen in value between pi by 2 and 3 pi by 2. But again, it goes up again. Why? Because the derivative here is positive. So the intervals at which there is increase or decrease depends on the sign of the derivative. Whereas the periods of convexity and concavity depends on the sign of the double derivative. So in fact here, the sine x, you will find that the graph is convex between 0 and pi, and this is why the double derivative is negative. Whereas it is concave between pi and 2 pi, and this is why the graph is the double derivative is positive. So this is the way how. Of course, here they are a little bit. You have to. I mean, they are confusing a little bit, but you may for a simple example of this sort, you may not. You may well it becomes a little bit intricate, but you have to visualize your curve. All you have to do is you, of course, for this function, the function reaches its maximum also at pi by 2, but it's not of our concern now. All our concern lies in the fact whether it's increasing or decreasing. Of course, if the function separates, if the function is separated at a point by two regions in which it's increasing then decreasing, we call this point maximum or minimum. If it's increasing and decreasing, it's maximum. If decreasing and increasing, it's minimum. But anyway, this is not, as I said, in our concern now. And this point at which x is equal to pi by 2, this is the maximum of sine. We know very well that the maximum is at the point pi by 2, and the minimum is at the point 3 pi by 2. But anyhow, it's increasing till pi by 2. So the f prime is positive, and then it decreases till 3 pi by 2, so f prime is negative, and then it decreases again, so f prime is positive. And same thing with the double, with f double prime, since it is convex, f double prime must be negative, and if it is concave, then f double prime is positive. And so actually, what we have exposed, what we have displayed in this lesson, we have actually talked of many applications. The first application is the how to calculate limits in a simpler way. The second thing, we talk about the convexity and concavity. And there is actually one way of showing this here if we want to speak about convexity and concavity. So here we see a cone which is being filled by water. We realize directly that the height increases indeed because you keep filling the cone with water. But there is one thing that you should notice, is that your curve here is convex. What does this mean? It does just mean, mean that your height, yes, increases, but the rate at which water fills the cone decreases. It starts by a higher rate and then decreases. Why? Because the area of the cross-section of the cone widens up. And because it widens up and your discharge, your water rate of spilling of the water into the cone is constant, and therefore you must have your second derivative of h must be less than 0, negative. In other words, you start with a higher rate of the h by dt, and then your rate lessens, and this is how, this is the meaning, in fact, of convexity. With this, in fact, we have reached the end of our lesson, and we have actually displayed a few notions, as I said. First of all, L'Hopital rule, and we said that in order to apply L'Hopital rule, you have to have the quotient of two functions which simultaneously tend to 0, and they are differentiable in a deleted neighborhood of the point at which you seek to determine your limit. So you can replace this by the derivative of both numerator and denominator separately. The other thing is that if you have other indeterminate quantities, unlike 0 over 0 or infinity over infinity, you just transform into these two indeterminate forms in order that your function be amenable to the application of L'Hopital. Again, we spoke of convexity and concavity, and I think this applet shows you very well the meaning of this. And of course, decrease of the inflection points, and the inflection point separates two regions in which the function is one, for example, is concave, then convex, or the opposite. And at this point, actually, the second derivative either vanishes or it's equal to 0. With this, we have reached the end of our lesson. And I wish to remind you again, like every lesson, that this lesson, together with the remaining ones or the one which have preceded, are all uploaded to the site of the MedNetU project organized by the Consortium of Nettuno. And hopefully it will serve all those students to prescribe to an engineering education. And until we meet in our next lecture, in fact, I would like to, and this lecture will also will speak again of some other application of derivative, the last one or the one before last. Then I wish to thank you for your attention. And until we meet then, good luck in your study. And I thank you very much for your attention. And until we meet, thank you very much.